This is Pre-Calculus, Functions and Graphs. I'm Mr. Stark. Thanks a bunch for joining me. We're on topic 4, which is titled Building Functions from Functions. And this is the first of 2 lessons, 4a, Combining Functions Algebraically. You can follow along using this document, so if you're ready to get algebraic, let's go. Combining functions algebraically is fairly straightforward. We just have to get familiar with the notation. You can see down below we have a column dedicated just for that. Okay, here are the functions we're going to use. f of x equals x cubed, and g of x equals the square root of x plus 1. We'll combine those 2 functions 5 ways: sum, difference, product, quotient, and a special challenge. The notation for the sum of 2 functions, f and g, is simply f plus g. It could also be written as parentheses f plus g parentheses x, which can be confusing because it looks like a product. Let's work down this column. The notation for the difference of 2 functions is f minus g, or parentheses f minus g parentheses x. And as you might expect for the product, we have f times g, or parentheses fg parentheses x. For the quotient, we have f divided by g, or parentheses f divided by g parentheses x. And finally, here's our challenge. Let's see what happens when we multiply g times g. Okay, that's the notation. So let's look at specific examples using the 2 functions that I gave you. The sum f plus g would simply be x cubed plus the square root of x plus 1. The difference would be x cubed minus square root of x plus 1. The product is x cubed times square root of x plus 1. And it's important to write that x cubed in front of the square root because sometimes you get confused on whether the x cubed would be part of the square root or not. And you might be inclined to distribute that x cubed, but just don't. For the quotient, we have x cubed divided by square root of x plus 1. And again, we might be inclined to do some algebra with this, but there's really no need. And finally, g times g is the square root of x plus 1 times the square root of x plus 1, which is equal to x plus 1. And now for the domain, which is really the most important part of this whole process. So for the sum, we have x cubed plus square root of x plus 1. We need to make sure that that x plus 1 inside the square root is greater than or equal to 0. And remember, we can include 0 because the square root of 0 is 0. The solution to that inequality in interval notation is left bracket -1, comma, infinity, close parenthesis. For the difference of the 2 functions, we have the same situation, the square root of x plus 1. So x plus 1 must be greater than or equal to 0. Thus, the domain is the same. And for the product, we have the same situation. X plus 1 is greater than or equal to 0, and it has the same domain. But for the quotient, we have a different situation. Not only must x plus 1 be greater than or equal to 0, we can't let that denominator be equal to 0. When x is equal to -1, there's an issue. So we have x plus 1 must be greater than 0, not greater than or equal to. That means the domain is an open interval, -1, comma, infinity, exclusive of -1. Lastly, we have this challenge, g times g. Okay, it's equal to x plus 1. That's nice. But what's the domain? Some might think because we have x plus 1, the domain is all reals. But because that function, x plus 1, is dependent on g, which has restrictions on its domain, then the domain of g times g is the same as what the domain of the original function is, which is -1, comma, infinity, inclusive of -1. Based on what we've seen here, I have 2 tips for you. Number 1, when you work with a quotient, be aware of those issues that show up from the denominator. Number 2, domains of combinations are dependent on the original functions. That's it for combinations. Next up is composition. Composing functions can be kind of fun, especially when you're dealing with just numbers. You take a number and plug it into one function, Then you take that output and plug it into the other function, and then you get a final result. Here's the definition of composition of functions. The composition f of g, denoted by f, this little o symbol, g, is defined by parentheses f o g, parentheses x, equals f of g of x, using parentheses. So we say that f of g of x. When we do the example, that will be fairly straightforward, but the domain requires a little extra thought. The domain of f of g is all x values in the domain of g that map to g of x values, so output values, in the domain of f. For f of g, think of g as the gatekeeper. It only allows certain x values in. But the gatekeeper also needs to consider what values work for f of x, meaning all of the outputs for g of x need to work as inputs for f of x as well. Okay, let's do an example with the same two functions, f of x equals x cubed and g of x equals the square root of x plus 1. F of g of x is equal to f of g of x, same wording, different notation, is equal to the square root of x plus 1, quantity cubed. Notice that g of x, root x plus 1, is on the inside of the composition, and x cubed is on the outside. Let's put in that extra thought about the domain now. In this case, g of x is like the gatekeeper. It's the first function that we're considering the domain for. The lowest value that we could plug into this function is -1. And -1 is okay because the square root of 0 is 0. Now let's consider f of x. Are there any values that we can't plug into f of x? No, we could plug in anything we want. So therefore, the gatekeeper just needs to worry about itself. So the domain of this composition of functions is -1, infinity, inclusive of the -1. The next thing we'll do is the composition in the other direction. So g of f of x, which is equal to g of f of x. Same wording, different notation. In this case, we're plugging the function f into g as x. So we get the square root of x cubed plus 1. Notice that if I asked you what's on the inside of this function, you could say x cubed plus 1. Or you could say x cubed, and the outside function is square root of x plus 1. So when we undo compositions or do a decomposition, there could be multiple answers. Time for some extra thought about the domain. So the first function we'll consider for the domain is f of x. Are there any values that we can't plug into x cubed? No. So far the domain is all reals. But in this case, f is the gatekeeper, so it needs to consider what output values it's sending to g of x. Since the smallest output that f can send to g is -1, we need to find out what input corresponds with that output. So what do we raise to the third power to get to -1? Well, that's -1. So therefore, -1 is the smallest x value that could be input into this composition. Therefore, the domain is -1, infinity, inclusive of -1. Many times you could find the domain of a composition by simply looking at the final function that you composed, but it's not always the same. So just put that extra thought into finding the domain of compositions, and you should be good. I have one final thought before you go. If you're finding the composition at a specific x value, like 3, you can do it two ways. You can find the composition algebraically, then plug in that 3. Or you could plug that 3 into the inside function, use that output to plug into the outside function. Either method will get you the correct answer. And that's it for lesson 4a. Thank you for combining functions with me algebraically.